Hello, friend. My name is Derek Harder, and in this video, we're going to continue talking with our discussion about convolutional neural networks. We're going to be looking at, to start with here, we need to get a little bit of theory, some background. So we're going to look at some modern convolutional neural network architecture patterns. Okay, so far in the examples of convolutional neural networks, we've used basic patterns. So there's a couple of more advanced ones that you really should know about. They're really useful to use. Okay, so let's go ahead and get started. So yeah, so far we've discussed the basics of how image classification and segmentation works, and we had an example of each of those. We didn't look at object identification, but we did look at an image classification example and a segmentation example. So the convolutional networks used in real world problems are not quite as simple as the ones that we looked at. Although we did, in our pre-trained example of using a pre-trained network, we used the BGG network, but also it kind of predated a little bit of some of the stuff we're going to talk about. Okay, so you're still lacking some of the mental models in order to be experts, or at least to begin to understand some of the more recent convolutional network architectures in order to kind of put together your own sort of state-of-the-art models. So to bridge that gap, for this first part in the section, we're going to look at architecture patterns for more complex use cases. So so a model's architecture is the sum of the choices that went into creating it. Okay, so we've discussed this at various points. So which layers to use, how to configure them, how to block them together, what arrangements to connect them in. So those choices define a hypothesis space. Okay, so it's the space of possible functions that gradient descent can search over. So by making those choices, you're making it harder or easier for gradient descent to learn and model the problem space. Okay, so those choices are the choices you make, and also the kind of the parameters you set are set by the model's weights. Okay, so this has some similarity to the idea of feature engineering that we talked about. In the same way, that hypothesis space that you set up by making these choices of layers and parameters and things, that's encoding your prior knowledge of the problem. Okay, so by doing that, you're helping gradient descent. So you're limiting it to make it easier to find a good model, so to find the correct manifold, so it will do well on learning your problem at hand and its possible solutions. So the correct architecture will make the difference between success and failure on a task. And you've already seen what we mean by that. A series of just dense layers is a lot tougher to get a really good model of on an image processing task. So there are assumptions that are built into convolution layers about the spatial nature of the inputs, right? Being spatially invariant and having kind of a hierarchy, right? So a good model architecture is one that reduces the size of the search space, and it makes it easier to converge to a good point of the search space by your optimization algorithm. So model architecture is all about making the problem simpler for gradient descent to solve, right? So if you have a good idea, good priors of your solution space, it allows you to make better choices about the architecture, so you can get better performance. So you may not kind of realize this, but gradient descent is really not a smart search process. It needs all the help it can get in order to get good results from it. There's not a lot of theory in this area here, deep learning, deep neural networks. So it's really still an engineering discipline. Okay, and I shouldn't say still as if that's a bad thing, but what really is that makes up the practice of creating deep neural networks is learning sort of the best practices that are part of the field that people have learned from experience, so that you can follow those and get the best results that you can, especially when you're just beginning out in this field. So in this video, we'll look at some of the best practices for developing convolutional neural networks in particular that you haven't seen before. So those include residual connections, which are directly focused at fixing what's known as the vanishing gradients problem. And we'll look at batch normalization. So batch normalization is another normalization technique that so you're familiar with normalizing data before you input into a network. So this is another type of normalization technique. And another type of convolutional layer known as depthwise separable convolutions. So just a little bit before we get back to deep neural networks. So in most engineering disciplines are really about managing complexity. So you have complex systems that you need to design or manage or build things to work within a complex system. So the general approach for most engineering disciplines that are involved with complex systems is to structure the complexity, so break it apart into individual modules, okay? So decompose the problem into smaller problems that are easier to understand and solve. Organize the modules into a hierarchy. So you've got things that are overall picture stuff down to small things that are dealing with the nuts and bolts that you need to worry about for your problem. And the higher level, you can hide complexity from the higher levels by relying on the lower levels to do basic things for you that you need. And then reusing those modules in multiple places. So this is a form of abstraction for your problem. So this is, in general, in kind of complexity theory, is known as modularity hierarchy reuse formula. So if you've done know some things about the area of software engineering or software architecture, this should be familiar with you. I was talking with a student recently about this. So an effective code base, so being an effective software architect should be modular and hierarchical, and you need to be very conscious that you're reusing as much as possible. You're not re-implementing the same things, okay? So that's what usually makes a good software architecture, so a good code base, that you're following these principles. You've decomposed it well, you've organized them from abstract to specific, and you reuse as much as possible within your code base. So deep learning is simply the application of this recipe to continuous optimization via gradient descent, okay? So you take the optimization technique, we're using gradient descent usually. You structure the search space in the modules, so that's kind of what the layers in a convolutional network are doing, is we're structuring the search space in the modules. We organize those hierarchically, so into a deep hierarchy. So we expect the first layers to be the simple nuts and bolts features that are learned and identified, and those get built up into more and more abstract representations or features. And then you reuse whatever you can. So that's kind of what convolutions are all about. That they're reusing the same feature and trying to identify that in different spatial locations on the image that they're working with. So deep learning model architectures, follow that same kind of pattern. They're making clever use of modularity and hierarchy. So most convolutional networks are pyramid-like structures of feature hierarchies, okay? And that was what the VGG 16, when we did our reuse of a pre-trained model example. So deeper hierarchies are intrinsically good. So being deep and shallow is much better for these kinds of problems than being non-deep and broad, okay? They encourage feature reuse and therefore abstraction in the models that they learn. So, looking at the VGG 16 model again, here's a visualization of it. So it looks like a pyramid. It's a hierarchy from specific features that are non-abstract down to more highly abstract features when it goes through this hierarchy and learns, low-level features, which tend to be edge detection kinds of things, down to the very high-level abstractions it uses to make its final predictions. But you'll notice that we brought this up before. It's really repeated blocks of the same structure. So it's repeated blocks of two convolutions or three convolutions followed by a max pooling in this structure for the BGG16. So we've mentioned the vanishing gradients problem at points in this class. Okay, so deep learning was originally thought that it would be unsolvable because of this so-called vanishing gradients problem. Okay, so as you know, in these neural networks, the forward pass is really a series of tensor operations from the input to the output. And then in order to update the weights to do the optimization, we use something like backpropagation, which has to go backward through this in order to figure out how to assign updates for the weights in order to minimize a loss function, right? So in that sense, it's backpropagation is just a chain being applied to these chain of functions. So the game is to adjust the parameters of each function in the chain based on the error on the previous output. But there's some noise. So each successive function in this chain introduces some noise. So after a certain point, the noise overwhelms the gradient information that you have. So at that point, backpropagation stops working when your network is too deep. So in practice, more than 5-6 layers don't work well. You hit this vanishing gradient problem. So your model just won't train at all because when you hit these vanishing gradients. So let's look at the first of these best practices, residual connections. So these are directly aimed at fixing the vanishing gradients problem. So the idea is relatively simple. So to fix the vanishing gradients, instead of relying on the signal, this noise that comes out, if we just had directly the untransformed inputs, this would give us a noiseless version of the information contained in the previous input. Okay, so the easiest way to do that is to, just like this figure shows, is to add in what are known as residual connections. So have the inputs do their normal things, going through one or more layers, blocks that are transformed by tensor operations to an output, but then having connections that just directly feed the inputs and combining those together with the output from a layer or a series of layers. So these act as information shortcuts around destructive or noisy blocks. They help give information to gradient descent that allows it to keep this vanishing gradient problem from happening. So in practice, if we're using like the Keras functional API, it's easy. So from the Keras API, we can easily create graphs like this for our network architecture. So it looks something like this. So, if X is our input, this is going to be the input to some block. So block here might represent, one layer or a sequence of layers. So we keep the input before it's fed into the block. And then there's a method, this part of Keras, that you can use to add, which will take the output from the block and the original input and combine those together. So the next layer that uses X after this will get a combination of both the original residual input and the transformed input. So it is a little bit more complex than that because the residual and the output that you're adding to have to have the same shape. So when you go through like a convolution or a max pooling layer, it doesn't anymore. So there's a simple trick though. So you can use a 1x1 convolution that has no activation, so it's not actually really learning anything, to linearly project the residual to the desired shape. So it looks something like this. So again, we get the residual, and then this original input X will go through like a convolutional layer, and then the residual will put through a 1x1 convolution. of the same number of output features as the layer that we need to add it together to. Right? So then the result of that is that X and the residual X, after we do this one-by-one convolution, actually have the same shape. So we can do the residual connection trick like we did before. Right? So in the case where your target block includes a max pooling layer, so a little bit, remember max pooling layers will downsample. So, but you can easily handle that. So the typical way to do that is to use strides. So in this block here, we do a convolutional layer, which is going to output 64 features. And then we put this through a max pooling layer, which will downsample 2 times, right? So our residual then, in order to match the shape, we will just use a single one-by-one convolutional layer. So that would match the shape the way that we want to get 64 output features. But we just use the strides feature to do the downsampling. So again, in one shot, this one will cause a residuals that has the same output shape that comes from the resulting max pooling, and we can combine those together. Okay. So let's make that a little bit more concrete. So here's how you would use the Keras API. So here's an example in order to do those residual connections. Okay, so this would be a rather relatively complete example. So we have a function here that we can call that will create a block. So notice that this function, each time it's called, will create 2 convolutional layers, and optionally will create a max pooling layer. But this is adding in the residual connections for us, okay? So anytime this is called, whatever X is to begin with, so that's going to be the outputs that feed into the input for this block here. So we save that as a residual when we create the 2 layers and potentially the pooling layer. And then at the end, we create the residual. So if we have a pooling layer, we simply use a one-by-one convolution and that strides trick that we talked about. So that will give us the right shape for the residual. If we don't have a pooling layer, and only if the number of filters, if the filter shape changed, we use just a one-by-one convolution with no stride. So in either case, then the result will be the same as the output from either the convolution or the convolution with the max pooling layer, and we can combine those together. Okay. So the reason why we have this function here in this example from our textbook, so notice we can build basically something like an exception network that we're going to look at in a bit here by just creating blocks. So reusing that function. So each time we call this function, we're creating 2 convolution layers and a pooling layer, potentially. Optionally having a pooling layer on there, right? So with all this, we're going to create one block that has 32 features as the result of the output from the convolutions, and then 64 and 128 as we normally do. And these first 2 blocks will have a pooling layer, so these will be downsampling 2 times each time from the original 32 by 32 input down to 16 by 16 and then 8 by 8. And then the filters are increasing as usual. So let's look at the result of doing that. So we might get a better feel. So you can see, so we start with 32 by 32. We have our 2 convolutional layers in the max pooling, so we end up with the 16 by 16. But some of these in here represent the residual connection that we make. So it'll be easier if we visualize this using the plot model, so we can see the actual network structure here. Right. So we can see for the first block here, it goes through the 2 convolutions of the max pooling layer, and this over here represents the path for the residual connection. So we take the original input untransformed, put it through the one-by-one convolution, so the shape of that is going to be the same 16 by 16, and we use the stride 2 here, right? So we can add those together. That becomes the input to the next block, and that also becomes the input for our next residual that goes around. Okay, so our second best practice that we will mention here is batch normalization. Okay, so normalization you've already run across this in this class and maybe in machine learning class. It's a broad category of methods. The basic, bottom line for normalization is you're trying to make different samples be more similar to each other. So normally, the normalization you're probably most familiar with is where we center the data and we normalize so they all have a standard deviation of 1 for input. Data normalization may be useful after every tensor transformation that happens in a network. So after each layer, or sometimes after some layers. So even if the data entering a layer is normalized, it won't be any more after a tensor transformation. So could normalizing intermediate activations help? And it turns out it does, although people don't really know exactly why. There's some debate about what batch normalization is doing and how it helps training. But we can add this. So it is common to add in some batch normalization for deep convolutional networks. So there's a batch normalization layer. It does similar idea to what the normalization that you're used to does. So, it centers the data and normalizes the standard deviation. It has to do that adaptively. It's a little bit more complex than that. It has to keep track of, because this normalization can change as you get different batches. So it has to do an adaptive, keep track of what the mean and the standard deviation are that it's using to normalize. So for one train of thought is that batch normalization is another thing that's actually happening with gradient propagation. So some people believe that the reason batch normalization helps in some models is that it's also addressing the vanishing gradient problem. So if you want to use batch normalization in the Keras API, you just simply specify, that I want to add in a batch normalization layer. So normally after like a convolution layer. So a little bit more than that. Batch normalization, because of the way it works, you don't really need the bias vector anymore. In fact, it can be a little bit harmful. And also, it's recommended that the activation function happens after normalization. Okay, so a typical way to use batch normalization is more like the bottom one here. So if we have a convolutional 2D network, we tell it that we don't want to keep the bias vectors, only the weight vectors. Notice we're not specifying any activation. So by hand, so that the result of the output of that goes to normalization, and then RELU activation is applied. Okay. So neither of these layers actually have any learning parameters, the batch normalization or the activation. So again, only the convolutional 2D has the weights that are learned, and these transformations just happen afterwards for whatever the tensor transformation is that's output from the convolution layer. So the final best practice we'll look at are depthwise separable convolutions. So this is kind of the most controversial. The author, I believe, is one of the people that kind of came up with these. So take that with a bit of a grain of salt. But there's evidence that these. So you can try just using separable 2D convolutions. So I won't go into the details exactly of how these work, but in kind of much the same way that a convolution relies on the assumption that patterns and images are not tied to a specific location. So doing one of these depthwise separable convolutions, it relies on the assumption that the spatial locations are highly correlated, but the different channels, so the different features that are being learned, are highly independent. Okay, so if and when that's true, you can do the same convolution operation can result, but you do them independently on each of the channels or each of the features. All right. So I'll just say, kind of the conclusion on that is that you can try these. Usually they won't hurt, and in some things they will help. So in some models they'll improve performance by a percentage, a little bit. Not to mention they usually are more computationally less expensive. So you get both maybe a bit of a less expensive model that might show a little bit more improvement over just using regular convolutions. So in the next video, I'm going to go into putting all these together. We're going to build a mini version of an exception model which use these concepts like residual connections, and batch normalization. But I want to end this video right here, so we'll do that in the next video. So in summary, some of these best practices that we talked about. So in general, your architecture for a convolutional neural network that's doing image processing should be organized into repeated blocks of layers, usually made up of multiple convolution layers and a max pooling layer. Okay, so you've already seen that pattern. The number of filters in your layer should increase as the size of the spatial feature maps decrease. So the number of filters increase as you go down the hierarchy, but the spatial feature maps decrease. Although that's a little bit misleading. They decrease the way we call them, like from 100 by 100 to 50 by 50 to 25 by 25. But that means when you project them back on the original image, they're actually looking at larger chunks of the original image because of that. So deep and narrow is better than broad and shallow. And then the three things that we talked about. So residual connections around blocks help you to retain information, and they can avoid the vanishing gradients problem. Okay, so advanced convolutional models always have these sorts of residual connections. Batch normalization, it's a little bit controversial how and why it works. So one explanation is it also helps with vanishing gradients. So often batch normalization in your models are useful. They help improve in performance. And then probably the most controversial, but separable, piecewise separable convolutions, they're a drop-in replacement, so they should do the same thing. They usually won't hurt, and they can help. So they're usually computational, less expensive, and they might actually improve performance. So you can consider dropping them in. All right, so that's it for this video. I hope you stick around. So the next one, if we went a little bit faster than that, we'll kind of put it together and show you an example of doing this for a real actual model using all three of those pieces that we just talked about.